Our second video in Chapter 7 is called Net Ionic Equations. To get to a net ionic equation, we have to write a molecular equation, and then an ionic equation, and then a net ionic equation. The net ionic equation tells us exactly what reacts in a chemical reaction, and it only includes the species in the reaction that actually undergo a change. Let's start with our molecular equation and write the ionic and net ionic equations for the equation that's given. We have barium nitrate plus lithium sulfate yields barium sulfate and lithium nitrate. This equation is called a molecular equation, even though you may notice we have all ionic compounds. It's called a molecular equation because the ionic compounds are written as their formula units. Now, we learned about electrolyte solutions in our previous video, and we learned that in aqueous solution, when your ionic compounds have these aqueous state of matter designations, they don't exist in solution as their formula units, they exist in solution as ions. And so that's what we do going from the molecular equation to the ionic equation. We write all aqueous ionic compounds as species that have dissociated into their ions. However, anytime you see a solid, a liquid, or a gas, you do not change it going from the molecular equation to the ionic equation. So let's show all of these aqueous species as being dissociated into their ions. We have barium nitrate. Barium nitrate will dissociate into the aqueous barium 2+ ion. I'm going to write my aqueous designations kind of underneath my ions because it will take a lot of room if I write next to them. And then barium nitrate will also split into two nitrate ions, NO3 with a -1 charge with that aqueous designation. Now notice I had to put that 2 in front of nitrate because it tells me that for every one formula unit of barium nitrate, I have one barium ion and 2 nitrate ions. And so I have to say that it dissociates into those ions. Something similar for lithium sulfate here. Lithium sulfate will dissociate into 2 lithium ions and 1 sulfate ion, SO4, with a -2 charge. So you can see it's very important to go back and refresh your memory on these polyatomic ions to remember the charges and to be able to identify their formulas. Alright, so we have our 4 aqueous ions on our reactant side. Next, on our product side, we have barium sulfate, but notice it has the solid state of matter designation. I can't split barium sulfate into its ions because it's telling me that it didn't dissociate, that it's not aqueous. So barium sulfate remains the same as a solid. And finally, my last ionic compound is an aqueous ionic compound. And that means I have to dissociate it into its ions. There's a coefficient 2 in front of it for balancing. That means that I have 2 aqueous lithium ions, and that 2 also carries over to the 2 nitrate ions, 2NO3- aqueous. So this is our ionic equation. We split all of our aqueous compounds into their ions and left solids, liquids, and gases alone. For the net ionic equation, we write only the things that have undergone a chemical change. To identify if something has undergone a chemical change, we have to first identify what does not undergo a chemical change, meaning that if we have something that's the same on both the reactant side and our product side of our ionic equation, that's telling us it did not change. For instance, we have 2 NO3 minus aqueous ions on our reactant side and 2 NO3 minus aqueous ions on our product side. Because we have the exact same thing on both sides of the reaction, it has not changed, and so we will not express it in our net ionic equation. We have another ion that has not changed, our 2 Li plus ions on both sides of the reaction. They have not changed, and so they will not be included in our net ionic equation. What has changed is our barium ion and our sulfate ion. They exist as aqueous ions on the reactant side of the equation, but they exist as a solid compound on the product side. So our net ionic equation is written as this. We just transfer all the things that have changed down to the net ionic equation, but we keep the reactant side from our ionic equation as reactants in our net ionic equation, meaning we'll write that barium 2 plus aqueous ion and sulfate aqueous ion as reactants, and then we'll carry that barium sulfate solid down as a product. So here's our net ionic equation. Everything that we did not carry down from our ionic equation to our net ionic equation has a special name. So these nitrate ions and the lithium ions, because they did not participate in the reaction, they're called spectator ions. And your spectator ions are said to not participate in the reaction, they just watch it. So they're spectators. Our next question is, what are the spectator ions in the following reaction? We have strontium hydroxide and 2 nitric acid gives us 2 water molecules and strontium nitrate. Well, to identify the spectator ions, we want to write the molecular equation, which is what's given to us. We want to convert our molecular equation to an ionic equation, meaning we dissociate all of our aqueous ionic compounds into their ions. And then from our ionic equation, we want to see what changed, and what does not change will be our spectator ions. So let's go through the process again. What are the spectator ions here? Our ionic equation will be the following. Looking at strontium hydroxide, we see an aqueous compound. That means that strontium will be a 2 plus aqueous ion, and we'll also have 2 aqueous hydroxide ions. We'll also get from nitric acid here. We'll learn more about acids in our next video, but what an acid does is it dissociates into hydrogen ions. Here we'll have 2 of them because of the coefficient 2 out front. And we'll also carry that coefficient 2 to the nitrate, NO3 minus. So on our reactant side, we have strontium 2 plus, 2 hydroxide ions, 2 H plus ions, and 2 nitrate ions. Looking again to see that both compounds are written as aqueous and they're ionic compounds, so we can split them into their ions. Next, we have our product side. Looking at our first product, we have water. It's written as a liquid. We cannot dissociate liquids into their ions. So water, also being a molecular compound, will not form ions. So I'm going to keep the 2H2O as a liquid, just as it's written in the equation. And finally, aqueous strontium nitrate will dissociate into strontium 2 plus aqueous and also 2 nitrate ions. Alright, so all my products are here, and then all my reactants are here. Looking at what has not changed, we have strontium 2 plus as an aqueous ion on both the reactants and the product side, and we have 2 nitrate ions that have not changed as well. Therefore, these two things are the spectator ions, strontium 2 plus, and nitrate. We can also write our net ionic equation. For the net ionic equation, we would write 2H plus 2OH minus yields 2H2O, but after writing the net ionic equation, we should notice that every coefficient is 2, and therefore that's not a correct way to express a chemical equation, because we can divide all those 2's by 2 to get 1. And so we can reduce the 2's down to 1, and it becomes aqueous H plus and aqueous OH minus will give us liquid water. Alright, so something to notice is that in an equation like this, where you have aqueous compounds combining to form a solid, as in the previous example, and a liquid in this example, as well as another aqueous compound, the ions that form the aqueous compound on the product side are the spectator ions. So we saw that our spectator ions are strontium and nitrate. Those are the 2 ions that make up our product, our aqueous product. And the net ionic equation shows how the product that's not aqueous forms. We had our liquid water, and we saw that the liquid water was formed from the combination of hydrogen and hydroxide ions.